Hey friends, this is Mrs. Walton. Ready to do some more systems of equations with you today. Today we are on topic 1 of solving systems of equations, and we are going to be introduced to our first method of solving, and that is by graphing. You guys had a little taste of this yesterday, and now we are going to go ahead and continue on with graphing. So I do want to go ahead and have a little throwback Tuesday, and by that I want to go back to yesterday's assignment when we were talking about our supply, how many people are applying for a job, and our demand. And we actually solved this system by graphing. We were looking for that intersection. So yesterday we talked about our supply equation. For every additional dollar, 24 more people were applying, and that was the point we were given. And then our demand, the company was going to hire 8 less people for every dollar. So we had two different equations here. We had our supply equation and our demand equation. Now, let's go ahead and talk about what it means to be a solution to a system of equations. Well, a solution is any set of values that are true for all equations simultaneously. So we are looking for an x and a y value that are a part of both lines. And sure enough, when we graphed it and solved, we found that 8.75, 210, that was a point that was on both our supply equation and our demand equation. It was perfect. It fit both. So let's go ahead and talk about what did this mean in the context of the problem, 8.75 and 210. Well, in the context of this problem, this meant that, where you going, buddy? This meant that we were looking for a rate of $8.75 per hour brought in 210 applicants, which matched the amount of people the company wanted to hire. So this was the perfect solution. This didn't have too many applicants. It didn't have too many people that the company wanted to hire. It was the perfect situation for both the applicants and the employer. And this was the intersection of these two lines. At 8.75, we had an output of 210 for both of those. And this is going to be true for any system of equations. If I have an intersection, that is going to be my perfect solution. So here is how I want to go about this. Mr. Parsons is going to pause the video here for a minute. What I would like for you guys to do is I would like for you guys to try to plot these two lines, and I want to see, can you find the solution? You might have a little slope-intercept form. It looks like you've got a standard form for the other one. But what I would like for you guys to try to do is go ahead and plot these two lines and find a solution that is on both of those lines. So Mr. Parsons, go ahead and pause the video. Let's see what you guys had here. So first off, for my first line, I had 3x plus y equals 9. Well, personally for me, I love to find intercepts and graph in this method. So if I was looking for the x-intercept, my x-intercepts, well, my y would be 0. And if I substituted in 0 for y, I'm left with the equation 3x equals 9. And if I solve that, I end up with an x-intercept of 3, an x-intercept of 3. So let's go ahead and plot that down here. I have an x-intercept of 3. Now my y-intercept, well, that was an easy one. If I plug in 0 for x, 3 times 0 is 0. 0 plus y equals 9. Well, sure enough, y has to be 9. So there we go. And if I connected those points, I would have a beautiful line. Now looking at this, I went down 9 over 3. That would mean I have a slope of negative 3. So down 3 over 1, down 3 over 1, down 3 over 1, down 3 over 1, and continuing on with that pattern. Now I do know that it only takes 2 points to make a line. However, we don't know where our intersection is going to be. So I went ahead and continued that on for a little bit. And I could go over here and graph that as well. My lines were 0, 9. I had 1, 6, 2, 3, 3, 0, 4, negative 3, 5, negative 6. I can keep on going, and sure enough, those go through that. Now let's go ahead and talk about my second equation. My second equation was an easy one that was in slope-intercept form. I had y equals negative x minus 1. Y equals negative x minus 1. Now this one was a pretty easy one. If I look at this one, well, sure enough, my y-intercept is negative 1. And boop. And my slope is, I just have a negative x here. Remember, that is an understood negative 1. So I'm going down 1 over 1, down 1 over 1, down 1 over 1. Ooh, we're getting close. We're zeroing in. Hey, and then we are right here. Now, if I were to go over here and graph this on Desmos, 0, negative 1, 1, negative 2, 2, negative 3, 3, negative 4. Well, I can't stop now. Yeah, now I can see my intersection. Sure enough, these two lines intersect at this value. So my final solution here is x equals 5, and y equals negative 6. Now it is important to note that you do need to have both a solution for your x value and your y value. For a system of equations, you want to know what is the point where we intersect. An x value isn't going to cut it. A y value isn't going to cut it. You need both of those. So we went ahead and found our solution to this one. We have x equals 5 and y equals negative 6. All right, so here's what I've got going on for you guys on this next page. We have examples 2, 3, and 4, and we might have some funky things going on in this example. So I want you to start to think about, before you graph these, I want you to think about, well, what if they don't intersect? What would that mean? What if they were the exact same line? What on earth would that mean? So what I would like for you guys to do, Mr. Parsons is going to go ahead and pause this video here in a moment. I'm going to give you guys, a good 5 minutes to work on these. And some funky things are going to happen, and that's going to be okay. It is possible that we don't have a solution to things. So go ahead, either by yourself or with a partner. What I would like for you guys to do is try to graph example 2, 3, 4, and then I would like to talk about what happens on those funky ones. All right, Mr. Parsons, go ahead and pause the video. Here's what I got. First off, for example 2, y equals negative 2x plus 3. We have a y-intercept of 3, a slope of negative 2. This should have looked like this. Y-intercept of negative 3, slope down 2 over 1, down 2 over 1. Over here, you could have solved for y, or you could have done this by intercepts. For this one, my x-intercept, if I were to solve negative x minus 4, negative x equals negative 4. I have an x-intercept of 4. Same thing with y. If I have 2y equals negative 4, that is negative 2. And my solution to this one ended up being 2, negative 1. So for this solution, you should have had x equals 2 and y equals negative 1. That is your solution. That is where both of those equations are true. All right, next example. First off, you had y equals 1/2 x minus 1. That comes as no surprise. I have a y-intercept of negative 1, and I have a slope of up 1 over 2, up 1 over 2, so on and so forth. For my second line, I have 6y minus 3x is equal to 6. Oh, well then, here's what I have. Those two lines, if I scroll forever this way and forever that way, those two lines are parallel. And sure enough, both of them have that slope of up 1 over 2, up 1 over 2. Up here, up 1 over 2, up 1 over 2, no matter what. I could zoom out forever. Those lines are never going to touch. So, here's the deal. If there's no intersection, the answer to this one is just simply no solution. There are no values of x and y that are going to make these two equations work. So the answer to this is simply just, hey, no solution. All right, and last one here. We have, for our first one, we have y equals 2/3 x minus 4. And for my second equation, I end up with this, 2x minus 3y equals 12. What? when I graph this, well, hot darn, those are the same lines. Now, here's the deal. We have tons of solutions for this one. We have 0, negative 4. We also have the point right here, 2.37, negative 2.42. We have this value right here. We have 6, 0, x equals 6, y equals 0. We've got 9.05 and 2.033. Now, you could spend the rest of your life listing out every single one of these solutions, or we could just say this. In this one, there are infinitely many solutions. Now, one thing that I want to point out here, this has infinitely many solutions. A popular catchphrase in algebra is all real numbers. That's not true here. All real numbers are not solutions to this. Yes, we have infinitely many solutions, but it's not all real numbers. Take this point right over here. X equals negative 2, y equals 2. That's not a solution. X equals 5, y equals 5. That's not a solution. So yes, we have an infinitely many solutions, but is it every single number in the universe? No. It's just a small portion of infinity of the larger infinity. That's a good philosophy question for you today. But here are different possible scenarios. We could have one solution, we could have no solutions, or we could have infinitely many solutions. So here is what you are going to be doing for homework. You have 1, 2, 3, 4, 5 just quick, easy questions in terms of graphing. Remember, you're either going to have one solution, no solutions, or infinitely many solutions. And you also have this page. We have some graphing systems applications, and this is where we're going to be starting up tomorrow. I'm going to go over these equations, but challenge yourself. See what you can do with this. So graphic systems applications, start to read through this and see what you can come up with. But that's where we are going to start tomorrow. All right, I hope you have a wonderful day. Please feel free to stop by and ask me any questions. Your main focus should be these 5 problems. Take a little look at these. Don't completely ignore them, but this will be kind of an extension for tomorrow. Have a wonderful day. Talk to you later.